What we're going to do today is build the Goodwin model of a growth cycle. Have you all heard of Goodwin's paper, A Growth Cycle? Okay, right. It was a model, fundamentally, that Goodwin saw in Marx. Has anybody here read Marx? A bit, okay.
The entire capital or just...
Well, yeah, I mean, I've read everything he's written on economics, so yes, Capital Volume 1 is where I'm talking about. And in Chapter 25, almost out of the blue, because in Volume 1, Marx basically holds constant money. He regards wages as being what he calls the value of labour power, which is a subsistence wage. Okay, and throughout the book, that's what he does. He also ignores money. He talks about gold, again for the sake of ignoring the monetary system, not because he believes gold is money. But he's leaving labour constant, and then out of the blue, there's this set of phrases discussing partly Adam Smith, that he says a rise in the price of labour resulting from accumulation of capital implies accumulation slackens because of the rise of the price of labour. So income just going to workers, less going to capitalists. The rate of accumulation lessens, meaning investment falls. Because that falls, there's less employment, so the employment rate drops. And because of that, the price of labour will fall, okay, back to a level which is consistent with the needs for expansion of capital. So capital will start expanding once more. And he finishes off with this little flourish. To put it mathematically, the rate of accumulation is the independent, not the dependent variable. The rate of wage is the dependent, not the independent variable. And there's reasonable knowledge that Marx spent most of his time after Capital trying to learn calculus to the stage where he could actually put this in mathematics. He never succeeded. But if he had done so, he would have beaten biologists by 50 years to what are called Predatorprey models. And Richard Goodwin was learning from a French mathematician who was an expert in what are called Predatorprey models. And what he saw in what Marx was talking about there is something similar to what happens in a model of predator-prey interaction. So the first case of this was actually fish and sharks, not off the coast of Australia, but off the coast of Italy during the First World War. And a statistician, biologist and statistician, was puzzled by the cycles that he saw in the number of fish and the number of sharks being captured by fishermen, which changed when a whole lot of Italians were conscripted to fight in the First World War. So he's trying to understand those dynamics. And he approached a mathematical biologist, a mathematician specialising in biology. So it's known as the Volterra model after the two people involved in it. And I think it was Volterra who came up with the first idea, saying that it had a large number of fish, and there's lots of food for the sharks, so the shark population grows rapidly. Because that happens, more fish get eaten. Because the fish get eaten, the fish numbers die off, therefore the sharks die off. The death of sharks means more fish get to eat food and stay alive and reproduce, and you get a cycle. So what I want you to do, as a preliminary message, step right now, is build a basic predator-prey model, or start building it. We won't finish it. Start building it in Minsky, because that'll give you a familiarity with the idea of how you show differential equations in Minsky, how you put graphs together and stuff like that. I'm using values from a model by another company called Insight Maker. And I'm trying to get this to, I want to make it larger. Not working. It's okay. Okay. So this is, oh great. Go back here again. So I just want to magnify that. There we go. That's it. Okay. So this is a predator-prey model in Insight Maker, and you notice how it's got these arrows running through. There's moose birth rate, the number of moose births occurring because of it, how many moose there are, the moose death rate, etc., etc. That's pretty much that's an open source, runs under your browser, so it's quite a easy program to use. But it's using the same modelling technique that Vensim uses, where you can't actually see the equations. You see the boxes, you've got to look inside the boxes to see what's going on. So I want to build that model and have you make your own personal comparison between that approach and what Minsky does as well. But what we're going to look at is two populations. So that was a model of wolves versus and moose. And you think, again, it's the same basic idea, but how did Volterra get his insight? Well, he basically said, what you assume in the absence of any predators is that the prey population will grow exponentially. So assume they've got a limitless supply of food to eat, okay, which is a bit extreme, but it's a starting point. So you have an exponential growth in the population. Well, the way you show exponential growth is say the percentage rate of change of something is a constant. It's 1 over x dx dt equals a constant, where x here is moose. And so the model is, the basic model, and this is using the numbers from that Insight Maker simulation as well, is that the rate of growth of moose per annum is 25%. In other words, effectively for every 4 moose that are alive, there'll be 1 born that year, and then that will compound over time. And the initial population they had was 426 moose. This is the calculator. This is using actual data from somewhere in I presume in Canada. Now, in the absence of moose, moose is one of those funny words which is a singular and a plural. Okay. In the absence of moose, the wolf population will fall exponentially. Nothing to eat, so they're going to starve to death. So what you have there is 1 over wolves to wolves dt is minus c, whereas c is 0.25. And that's, again, that's quite a low number. That's about the 1 death per 4 wolves per year. I'll edit that later. It's the sort of mistakes I find when I'm giving a presentation you don't spot when you're actually designing the slides. And the initial population of wolves is 20. So enter these in Minsky. What you do is first of all you express it as a pure differential equation. 1 over x dx dt is a percentage rate of growth. Okay? That's the easy way to think about what exponential growth is all about. What you do is multiply through by the 1 over x. So here is 1 over x is 1 over moose. So what you say, the rate of change of moose is a times how many moose there are. Okay. Now in Minsky, what you do, this applies to all system dynamics programs. You don't enter the differential equation directly, because in all these programs they use integration instead. And the reason for that is integration is a smooth, I don't know, my voice is gone, this one I have to get some water. Integration is a smoother process than differentiation. If you imagine you're walking up a mountain, okay, then the area, if you took a cross-section of the area of the mountain as you're walking up, it's not going to change a lot as you change your altitude. But there's going to be huge variations in the slope of the mountain as you walk up and down. Well, those variations are really extreme. The change in the area is much more gradual. So numerically, integration is a smoother process than differentiation, so the programs all work with integration. So what you do is you integrate. And that's showing you, if you look at what's going on here, this is saying there's moose over here, there's an integral sign down here, a times the number of moose, a times the number of moose. So what I want you to do is simply mock that up in Minsky and see what happens. So I think I'll show you what I did, just running it as a little movie here. So you bring an integral block down, choose edit, give it the name moose, click on OK, create a parameter, call it A, which is it's a simple way of putting it together. Give it a value of 0.25, may give a range of maximum of 1, minimum of 0.1 and a step size of 0.05. And then you can take a copy, right click and take a copy of the variable moose, drag it over that side, choose the multiply key, drag them together, link it up to the top of the thing. Now I'm just typing moose _ 0 directly under the canvas, and that creates a variable which is the new, so moose 0 means moose at time 0, giving it a value of 426, making it into a parameter, and giving a range of, say, 1000 as a maximum, I think I gave 100 as a minimum, and a step size of 20. And having done all that, click on OK, drag. I notice sometimes Minsky makes it hard to grab an item when they overlap. Take a copy of that, put it down here, click from the little circle. You see the circle turns up if you join objects together. That's the initial condition. Drag a graph down, drag it out a bit, expand it, drag into one of the inputs. There are 4 inputs in that size. Press run. Okay? So what we want you to do now is do that. Okay?
Okay.
I'll go get a drink of water in the meantime. If you want to make it larger to see more easily on your screen, then let's see. That's a finished model here. But what you do is just click on that's going making its full normal size. That expands. And that contracts. So if you want to make it larger to see, just working on it, just click on that and make it a bit larger. I'll load my, where are we? Let's see. There's my finished model. And if you hold the shift key down and drag, you can drag it into the middle and hit the plus key here. Make it larger with the hassles in the beta version. The graph will disappear on occasions, unfortunately, but that'll make it easy to see what you're doing. And you can drag items around, as you can see. Click in the box away from the circle, you drag them around. Click on the circle, you drag a pointer out.
So yeah.
Now that's okay. Oh yeah, one little trick as well. The one of you has found by accident that there's a feature of Minsky which should look like a bug. I'll just do it in my machine here. At the moment, of course, this model works. But you can also notice if I drag an object around and I then touch where the wire is, a little blue dot turns up. That's how you can change the shape of the wire. Okay, that sort of thing if you want to. You can also right-click and choose straighten, which I'll do here. And I can also delete the wire just by highlighting it and pressing the delete key. But you can actually wire you can wire more than one thing to an input of a multiply key. And the reason being, you can multiply lots of things together at once. Okay, you don't need to add extra ports to multiply them together. That's one little feature we've got in Minsky, which just makes it easier to put a large model together. But for the meantime, it's just easier to multiply, top and bottom like that. It doesn't matter which one you put top, which one you put bottom, so long as you attach the multiply block to the top of the integral sign, which is what you're integrating, and the initial condition to the bottom. Okay, so have you all got that now? Still getting there? Let's see. So we had a couple of bugs. Done. Working okay? Good. Fine. Okay.
Which email address? ranking@gmail.com.
Yeah, that's right. Yeah. Pop it through to there. Okay. Hang on. Okay, well that's the basics. Some of you struck bugs in doing it. It's fascinating how people can produce them. What have you got?
I have not come to that point yet.
That's the basics of building a simple, the beginnings of a dynamic model. Now, I might get to, given it's taken us still 9:30 to get to that point, I might jump over doing the wolves right now. That's the basic idea is. That's how you enter differential equations in Minsky. If you take a look, if you've got a functional version of the model, click on the equations tab. And you'll find what you've got is shown as a different set of differential equations. Moose at 0 is 426, that's the parameter. Moose at bracket 0, which is times 0 for the actual variable moose, is also 426, because you made that the initial condition. And the rate of change of moose is A times the number of moose. Okay? So that's what Minsky is constructing for you and simulating in the background.
But isn't moose 0 rather a constant?
But moose 0 is a constant.
It's a constant.
That's a parameter. Okay, but moose underscore 0 is a way of indicating its initial condition in that sense. Okay, so having done that, you've now got a functional system. Now, I won't get you to finish this now. I'll get you to come back and try it later. But what Lambda and Volterra worked out was the simplest way to say that predators eat prey and that prey therefore the prey depend upon the predator and vice versa, in a sense, was that predators linearly reduce the growth rate. So rather than the growth rate being A, it's A minus B times how many wolves there are. And then for the wolves, prey increase the rate of growth of predators. So what you get is, rather than being minus C, it's minus C plus D times how many moose there are. And that gives you the overall equation. So we'll do that at a later stage, okay? Just because I want to get on to doing the economic modelling now. So let's skip to Goodwin's growth model. And I've made a mistake on that in a minute. We're going to make you do one more model now, but this will take a bit of time to do, but it'll give you a feeling, not just for building a model in Minsky, but also what complex systems are actually about. So I want you to build that model. Okay, so it's, the variables x, y, and z. So you have dx dt, dy dt, and dz dt. The constants are a, b, and c. Okay, and the initial values are minus 10, 10, and 30. And I'll just show you. I'll start building it. So bring up a blank Minsky here. So the fastest way to do, one way to do is click on the integral block, bring it down, double click, or choose edit and say that's A. Oh, sorry, that's X, pardon me. There's X. And I'll just make it larger, because it's easy to work with larger icons here. You can do this, click again on the integral block, drag it down, double click, make that Y. Now, another fast way of doing it is type the ampersand key, because what we do is we use the keyboard to create characters that look like mathematical operators. An integral sign looks like an ampersand. So if you hold down the shift key and press or whatever is ampersand on your keyboard, that brings up another integral block straight away. I'll double click on that, make it Z. So that's X, Y, and Z defined. Okay. And then I want 3 parameters. And again, a fast way to do it is I type the letter A, just type it anywhere on the keyboard. Minsky then pops up the define window here. So I'm going to say make that a parameter. And the initial value of A I'm using here is 10. Just type in 10. I've got to type in 10, type say 20 for a maximum and a minimum of 1 with a step size of 1. That's fine. That's A. And then B, same story. I think what's B's value? B is 28. So parameter, value of 28. So give a maximum of say 40, minimum of say 1, step size of 1. That's B. And then C is 2.67, so type C, make it a parameter again, 2.67, I'll just check that. Yep, and say a maximum of 4, minimum of say 0.5, and a step size of 0.01 because we're working in hundredths there. Okay, that's A, B, and C defined. And now all I need to do is make up the equation. Now, the important rapid trick with Minsky is you want to have, you can see, look, I've got dx dt equals A times y minus x. B, and I've got z minus y down here and y and z over here. So I need to have x, y, and z as variables. So you simply right-click on the integral block and choose copy. Right-click, choose copy. Right-click, choose copy. And I can make as many copies as I like of each of those and just relocate stuff on the screen. So I'll just do the first equation. The equation for x says dx dt equals A times y minus x. So I'm going to have y minus x here, so I just rearrange them. Press the minus key, I've got y minus x. I need a multiply block. Blocks, let's type the multiply key. Take a copy of A. I could just use the actual A that's up there. So A multiplied by y minus x is equal to x0, and then I have to have the initial values x0, y0, and z0. So again, the same story. I'll type x underscore 0 just to indicate it's the initial value. I could type it just down at the bottom there, but by having it up at the top, I can change the values very easily. So that's going to be 10. Let's say give a maximum of 15 and a minimum of say minus 15 with a step size of 1. and I didn't make it a parameter. I don't have to make it a parameter. It's just more logically correct to set it up that way because it doesn't get changed by anything else in the system. So there's x0. Take a copy of that, bring it down here and attach that to the bottom of the integral block. And now what I've got over here, if you look at the equations I've defined, I have x0 is equal to 10, dx dt is a times y minus x. There are my initial values. So I've almost defined the model. Okay? I know I'm probably a lot faster than you guys are at doing this, but you can do it pretty rapidly once you get used to it. So just do the same on your computer. That's x defined. Do y and z.
How do we get the x0? So if you copy something, you get
da kann ich auch
Let's just drag it out of the way, we'll leave it complicated there. That's correct, you've got x0 defined. You don't need to have multipliers like I just making it possible to modify different points. That's correctly defined. So not just a fixed that wire up, delete the push delete there.
Seem to fit.
Yeah, delete.
delete. What do you mean?
Right click on the wire. Delete wire. Wire at the top of the block, just underneath us.
This.
Why is the top of the block?
Yeah, there you go. Okay, so that's correctly defined. Oh no, that's wrong. So drag the x away. Yeah, just drag it away. Delete that wire. Attach it to the bottom.
Okay, which one is
The
it?
equations.
I can
Make sure that was correct.
Yeah.
Oh yeah.
You simply have to get
Right, you're getting there.
Okay.
Could you put up the slide with the...
Of course, pardon me. Yeah.
I think that's one done.
I don't know where it is.
Let's see.
Yeah, it doesn't matter actually.
Yeah, okay. I just wanted it to be where
Some
the
stuff
other-
I've skipped over here. Okay, there it
Well,
is.
I can do it later.
You're
So,
right, yeah.
so. Okay.
Yeah, no, you can start it. Yeah, no, you have to do it all again. Then it's fine.
I did this
X
one.
times b
Do it again.
minus
I got the wrong value for y there. X there, but I'll fix it up in a second.
No. Yeah, that's what happens sometimes.
Oh, okay, oh no. Good timing.
Yeah.
These are the new glasses.
It's so small.
Show your glasses.
Yeah, sure. I look on
So you're all doing it on your own machines?
Yes.
Okay.
I did until my PC broke
Yeah.
down.
X multiplied, okay, by b minus z. So take a copy of b. Multiply key. And then minus y. Minus key.
Do you remember anything? What's the initial values or something?
And then z. Let's see.
No.
What? Actually?
Yeah.
No, I don't
No,
remember
right.
anything.
Yeah, I can look at it.
It was too fast to remember.
What do you mean?
Oh, yeah, okay.
Yeah, no, I need to copy those, right? But if
Yeah.
they are not like correctly, you know what I mean? It's not the initial value and stuff, so I need
Yeah,
to
that,
copy it because then I have to do it again probably for all
So let's see how much is left. Maybe I'll just go with the older version.
Maybe, yes. But probably then you will always come to the point where it does not work.
Bugs, yeah.
again. So, I don't know.
I have a choice between my PC.
Now, when you've got something finished, give this the name Lorenz, Lorenz, Lorenz 01, for example,
Let's see.
your first version of Lorenz. So, is anybody close to that yet?
No.
Isn't it working?
That's the old one. That's the old.
I'm going to
Yeah, the new one
Okay.
didn't even start to download. Let's see what files I have. No.
I'm going to graphics instead. I went
Oh,
to
so
listen
it's
to you guys already.
Yeah, it's only the old ones. Okay, I have to start again.
Yeah.
I'm gonna give it a try. What was it? Documents. Name. Download. Oh, there we go. Accept. Next. So let's see.
Okay. What are we doing?
My PC broke down and now I have to.
Now he's going to get
Oh,
the
it's all in
beta
beta,
version,
good.
and
Okay.
I have
Yeah.
the beta version, but
Okay.
now I'm kind of lost.
Getting pretty close there?
Kind of lost.
That's it, yeah.
Okay.
Just make the, that's better, yeah.
That's good. So what?
Again, the other one.
Yeah, wait for it. It said wait.
When you make the graph larger, we're still working on this particular way of making things larger. But when you click click on a graph, then it's not reliable. But ultimately, the little arrows will turn up, and you can drag them out and make them larger. Then you get this bug that's currently in this beta version where it goes blank. Make it a bit larger; it'll work properly. That's a Windows bug, by the way. One of the hassles with Minsky is we're making a cross-platform, so it runs on Mac, Linux and Windows, and they each have different ways of addressing the screen. So even though it looks easy, it runs on 3 machines, you've got to have 3 separate sets of code to handle how it writes to the graphics processor, and this can cause all sorts of stuff up, and you've got bugs that are specific to particular operating systems. So you've got to spend a lot of time just going through working out what the hell's gone wrong with this generic command that for some reason is not working in that particular monitor. So, yeah. Yep.
It's saying X input, not Y input. Input.
Let's see. Show me the error message again. X put input, not Y to pen 2. Okay. Maybe. This is one little trick. I'll just show you on my computer up here.
So what was X?
Notice how on the graphs there are 4 coloured inputs here,
Yeah.
4 coloured inputs there, and 8 down the bottom. If you simply drag one to one of the y-axis ones, you get a graph against time. If you wire one against with the top and against the bottom, but they've got to be the same colour. Okay? So delete that Y and put it onto the same colour.
Okay. Ooh.
Now is it working?
Yeah.
Let's see.
Everything is an ink.
Beauty! Okay, that's what I want you to see. You want to turn your computer around and show the others, then you might be the first to get there.
Okay.
That was cool.
Okay. Now would you imagine,
What it means? I don't know. I just,
Yeah,
would you imagine that as simple a set of equations as that
communism.
generate behaviour that's that complicated? Okay? Now, that's a very rough simulation, by the way. If you go, notice up here is a Runge cutter. Runge cutter is a estimation system. It's a way of getting an approximate solution to dynamical equations. You can change various parameters and make it slower but more accurate. So the maximum step size is 0.01. Like let's say 0.001. Click on OK, and now let's run it again. It's still pretty ugly. Okay, what's wrong there? Runge cutter. Let's see. Relative error, make 0.001. Let's give that a try.
What is it?
Still pretty dreadful. I'm not quite certain. Well, that's should be better than that. Let's see. Absolute error 0.0001. Let's try that. No, I can't make anything less than dreadful in estimating. That's quite an ugly plot of Lorenz. What I want to do, I'll compare it to one that I've done previously over here. So this is two elements of Lorenz. What you're looking at was the initial model of nonlinear meteorology, built back in 1963. And the guy who developed it, Lorenz, Ed Lorenz, was a mathematical meteorologist. And at the time, everybody was using linear equations or pattern matching to predict the next day's weather. So they have a linear set of equations with all sorts of parameters, and given these values today, they'd make an estimate of tomorrow's weather. Or they'd use pattern matching and say we had this pattern of 5 days in a row, so the next day is likely to be like the 6th day, that sort of thing. And Lorenz's point was the weather's incredibly non-linear. We know that the interactions between temperature and moisture and altitude are all very, very complex. And actually they're called the Navier-Stokes equations. And they're amongst the most complex equations in mathematics. I think there's about 11 dimensions to it. Now he reduced this to a set of 3 ordinary differential equations in x, y, and z. And what this is representing, if you imagine having a pot of water on a stove, then you're tracking where one molecule of water is, effectively, given a temperature gradient. So x and y are the x and y locations on the hot plate, and z is the temperature differential between the top and bottom. It's like a very, very thin plate, like imagine a single drop of water. Where's it going to move, and what's going to happen to its temperature as it moves? Okay? So that's what those interactions are. Now, when he first did it, he had a computer that worked in 8 digits of accuracy internally, with a printer that printed out in 4 digits of accuracy. So he got this crazy pattern first time he saw it. He gave it back to his assistant and said, re-enter these numbers. But the numbers he re-entered were 4 digits long, whereas the machine was working with 8 digits of precision. So he was wrong by 0.0000 something. And what he got back when he ran it was a completely different pattern. So I'll show you that. This is, if you look here, that's all working in terms of x and y. I've got exactly the same equations in terms of x1 and y1 down here, with an absolutely tiny difference in one of the initial conditions. Same parameters. So I run this. It's a much smoother simulation, as you can see. I've got to check and see what the Runge cutter parameters are that make that difference. Now we're looking at number of seconds so far, but 10 seconds have passed so far. Where's this drop of water? Notice they're starting to diverge. Now, completely opposite patterns. So you have an incredibly small error and an incredibly huge divergence after a finite amount of time. And this is what they talk about, sensitive dependence upon initial conditions. Okay? The patterns are very much the same. That's the pattern of the XZ for the Z simulation. That's the pattern for the Z1 simulation. So the same pattern, but the time path is completely different after a finite amount of time. This is what's called chaotic systems or complex systems. That's what we're using Minsky to build. Okay? So I think we might, given our time, again, we'll leave it at that point for those who haven't got quite that far. 1 down, which is good. 2, cool. Okay. We'll copy all these around so you'll have the other files later. But that's an idea of just how complex A very, very simple looking model is. Now you take a look at the equations again. Let's just take a look at the equations inside here. All you've got are 3 constants and 3 variables. X, Y, and Z, A, B, and C. And they're simply multiplied together. There's no squares. There's pseudo-squaring going on because Y times X is like a pseudo-squaring of variables. You're multiplying one variable by another. So it's non-linear. But there's no sines, there's no tans, there's no logs, etc., etc. It's an incredibly simple function. But it gives you this amazingly complex behaviour. Okay? And that's the idea about complex systems. It's not that they're complicated. It's that they interact with each other in non-linear ways, and that gives you complex patterns. Okay? And that's the essence of the complex systems approach. You don't need a really detailed, complicated model to get complex behaviour. And often a simple model, and this is incredibly simple, shows you the underlying features of the system you're working with. So if Lorenz had tried to build the model of meteorology using the 11-dimensional Navier-Stokes equations, apologies to physicists who know the actual number of dimensions who might watch this video, but a huge number of dimensions, partial differential equations, simply beyond any possibility of a computer back then in the 1960s coming anywhere near simulating it, and even today that's a huge challenge. But by cutting it down to its essence, he found the fundamental instability of the weather system. Now, maybe we can do the same thing with economics if we abandon the obsession with equilibrium. And just to point out that particular detail, I'll do this in other presentations. I'll send you some data on this if you like later. Where the cursor currently is one equilibrium in the system. That's the second, and that's the third. Notice the system is nowhere near any of its 3 equilibria. In fact, the equilibria, they're called strange attractors because they both attract and repel. Okay? Because they attract, they keep the system bound that you don't get crazy values, okay? Negative temperatures and things like that. What you get, though, is a system which has complex, far from equilibrium behaviour. Okay? So the whole idea you can model the system in equilibrium is a joke. Now, when Lorentz presented this paper in 1963, meteorologists were very impressed and said, okay, let's start doing it then. 64, 65, you started getting the developments of the weather systems we now watch on TV. And if you watch any of the predictions about where cyclones and hurricanes and so on are going, it's not by far not the only part of how they make those models, but it's an essential part of how those models are built. And look how accurate their predictions are now. Okay? Think about the number of lives that would have been lost if Cyclone Sandy had been predicted using the pre-chaotic systems interpretation of the weather. They would have had no idea where it was coming ashore. They couldn't have evacuated all the people who might have been affected. Many, many more people would have died courtesy of that. So acknowledging that the weather is a complex system has been a major reason why our predictions of weather, our understanding of the climate, are far greater than they were 50 or 60 years ago. Economics, on the other hand, has gone backwards. So let's take it forward. So, and just to make a couple more points, there is no exogenous shock in that model. Okay? That is completely deterministic. And yet, it will never break down. It will never give you crazy values. And it's what's known as non-ergodic. Now, ergodic is a word that's been abused in economics by people that don't understand what it means. Most people don't understand what the word means, so I'm not being too critical of economists to say that. But it fundamentally means your statistical average is not going to be the same as your time average. Okay? The statistical average would be, if the statistical, this is looking at the time pattern of the Lorenz model. Now, even though it's following a very, very complicated path, there are parts of the phase space it goes nowhere near. It's repelled from the equilibria, and it goes nowhere near these regions here. So the time dimension is quite different to the space dimension. That's the fundamental thing about non-ergodic systems. And that has important implications of whether you can use statistics, past statistics, to predict the future behaviour of a system. With a non-ergodic system, you can't. Okay. Again, that's the point of this comparison of two time paths of the system. If you tried to use past behaviour to predict the future, after a certain time your past behaviour gives you absolutely no guidance as to where the system is going to be. So you've got to have a sliding window. And the question is, can you make the sliding window long enough that you can make decent predictions? In the weather, it's about a week. Okay? Huge amount of computing power to take it beyond a week, which has probably been done. But that's the sort of intelligence and knowledge about complex systems that is commonplace in a genuine science like meteorology. So all this stuff is easily accepted by non-economists, but the equilibrium fetish that economists have means they just simply don't look at it at all. Those are two more models, by the way, that you might enjoy looking at. So I've embedded those in the presentation. I'll give you those at the end of the course because I'm still writing all the lectures. So let's take a look at non-equilibrium economics now and get started on that at least. So the basic logic in Marx's model was that, first of all, capital determines output. Okay, you have investment occurring, accumulation and so on. Output determines the employment level. The rate of employment, which is employment divided by population, determines how fast wages change. Wages determine profits. He's got a two-class system here. There's only capitalists and workers. So output minus wages is profits. Profits determine investment, and investment is the rate of change of the capital stock. And that's the essential idea of a dynamic model. You go from a current value of something, current or lagged, to a rate of change, and you get back to the same thing again. And you close the loop. And that's what you can see in a model like, not so much like Lorenz, but you'll see in this model of Marx's model as well. Now, Marx thought this would cause cycles. He didn't say we'd converge to equilibrium, okay? But he was only making a verbal intuition. The question is, was he right? Well, let's find out. So, the simplest way to build the model is to use linear relationships between the variables. And again, that's the point of the complex system. All the relationships between the variables here are linear. If you take a look at the equations in the Lorenz model, it's A times 1, like I said. It's not A as a function of X or anything like that. It's just simple constants, okay? And yet it gives you that incredibly complicated behaviour. So the non-linearity is not because you've got nonlinear behaviour imposed on a linear model. The model itself is nonlinear. Okay? And one point one of my colleagues in this industry makes is it's saying something is nonlinear is saying a bit like saying an animal that's it's sort of like talking about non-life. Okay, every animal is alive. There's no such thing as a non-alive animal. Well, non-linearity is similar. Everything's non-linear. We approximate systems with linearity in various times, but fundamentally everything is non-linear. If you're walking up a straight hill, it's non-linear because at some point it'll stop or you'll walk off the planet. Okay? Since you can't do the latter, it's non-linear. There's a break. And every relationship we look at is actually non-linear in its essence. But the non-linearity is embedded in the system. It's not imposed by your behavioural assumptions necessarily. And when you bring non-linearity in, which we'll do later, you do it to make it more realistic, not to give it its dynamics. So you find most of what you need with simple linear relationships. Let's give it a try here. So capital determines output. The simplest argument for that is an accelerator relationship. Your capital stock divided by capital output ratio gives you how many units are produced. So that's your equation relating capital stock to output. Output determines employment, so we'll divide employment by labour productivity. I don't like that term, by the way. I want to abolish that term, but that's what we call it at the moment. You get how many workers are hired. Divide that by population, you get the employment rate. Then the employment rate determines the rate of change of real wages. In this case, we're working with real wages. And this can easily be modified to make it into money wages. So what you're saying is the percentage rate of change of the real wage is some function of the employment rate. And that's the percentage rate of change of real wages. That's a function of the employment rate. To make a linear one, what I use is a very simple function. Phillips insisted on a non-linear 3-factor function, by the way. Most economists haven't got a clue about that because they haven't read Phillips. They never read the originals. They read their own stupid textbook versions of everything. So what I use here is a very simple function saying the employment function is the slope of the function multiplied by the current value minus a 0 point. So that bit is where wage change is 0. That bit is the slope, how much workers react to a difference between the actual employment rate and the 0 point, and that's the actual, that lambda is the actual employment level. So a pretty simple equation. Now the wage rate determines the labour. Once you've got those, by the way, you've got all you need to complete the model, because the real wage times labour determines the bill in real wage terms in this model. Output minus the wage bill gives you profit. And the simple assumption that Goodwin made, which we're going to change later, is that all profits are invested. So profit gives you investment. And investment is the rate of change of capital stock after depreciation. Okay? So you've closed the model. You've started with capital determines output. Okay? You finish up with the whole thing. So there's a causal loop. You say capital divided by the output ratio gives you output. Output divided by labour productivity gives you employment. Employment divided by population gives you the employment rate. Feed that into the Phillips curve, as it's called. You get the rate of change of wages. Multiply that by the wage rate. That will give you, and integrate that will give you the actual wage. Multiply the wage by employment, you get the wage bill. Subtract that from output, you get profit. Assume all profit is invested, which is Goodwin's simple assumption. Subtract depreciation, you've got the rate of change of capital. That gives you the capital stock, you're back where you started again. Okay? So this idea of a system dynamics program is putting that causal loop together. So let's use Minsky to do that. So here are your parameter values. You can define all these straight away. You can do any order you like, but it's probably best to put the parameters in first of all. So V of 3, the slope of the Phillips curve of 10, an employment rate of 0.6. When 60% of the population has a job, there's no change in wages. Depreciation rate of 10%. Treat labour productivity and population as constants. We'll change it later, or as make them parameters. Of course, they've got to be parameters for you to be able to give them a name. And constants are just called, 1, 2, 3, whatever else. So use 1 for A, so 1 unit of output per worker, and N 120, so population is 120. And have initial conditions, 300 units of capital, wage rate of 0.8, and build the model. Now, I'll let you take those constants down first of all. On a roll back.
In der Leitungssprache einfach Lambda
Ich habe eine ganz normale
BDA.
diese Lambda. Ja, genau.
What I might do is whack those parameters up here. So you can see them on the other screen.
Ah, jetzt denke ich mal.
Weiter. Ja.
Warum habe ich es denn geschafft? Achso, das war ein falschen Strich. Das muss in die andere Richtung.
Okay.
Das ist geil, ne?
The value is there. Now,
Das ist eine Gänse.
okay. Oh, lambda, by the way, didn't it? If you say LAMBDA and underscore and say capital S, that's Minsky converting the tech word for lambda into the Greek letter. So I'm going to give that a value of 10 there, maximum of 20, minimum 1, step size of 1. And there's lambda underscore capital S for slope.
I know I do.
Okay.
The value for delta K is 0.1.
0.1, yeah.
We need to create the without
Yeah.
Das ist ein kleines Delta, glaube ich. Aber
Steve, could you quickly show the Phillips equation?
Yeah, that's it.
Yeah, sure.
So the Phillips equation, I'll write it up on the board over here. We call it PC if you like, lambda, but it's equal to lambda capital S multiplied by lambda
As in brackets.
minus lambda
But the
capital Z.
these kind of brackets, the big ones with this one.
Leave A as a flow, by the way. Don't change it to a variable, to a parameter. Leave it as a flow. I'll show you why in a moment. So the difference between a parameter and a flow is a flow has an input and an output. A parameter just has an output. Okay? And the same for N. Pardon me. So those are, just going to save that. Sometime, looks like there's another error here. I'm typing Control S and I'm getting a, Control S is supposed to be a shortcut for save. And let's see. Because it's Control capital S, the program wasn't recognising it. A Control lowercase s, that's not an issue bug, it's just we haven't set the feature up properly. It should be not case sensitive. So I'll call that Goodwin live 01. Yeah. Now, one thing which may not have been clear, I'll just actually page down here and take a look. Outside the slideshow, let's see. Okay. I'll leave this up on screen because that's probably the most useful way to see the overall model. And notice you're going, there's an integral equation for capital and there's an integral equation for the wages. So you need to have those in your model, and I'll just show you how to do that quickly. Fast way to do it is to just type, either click on the integral block here, bring it down and make that K, which is going to be a capital integral block. And just the fast way of doing it, type the ampersand and make this W underscore little r, or should give you a subscript of r. So those are your two integral blocks. You have to have those as part of the model. So I'm going to save that as the second file in this sequence. And now I can define the rest of the model from that point. So you keep on going. It's always good to make mistakes in this stuff because it's partly how you learn. If you don't knock it off during the class, try doing it yourself later, tonight or whenever, on your laptop and get it right. Okay? Don't just rely on my copy. Do it yourselves because it's a major way you learn how to do these things. So I'm going to start. I'll just start defining this one now, and you can see what's going on. If you use the annoying square, that's to help you move the screen around, which is useful. But you'd rather have a pointer, just press the Shift key. That's been a long-standing bug we haven't got rid of. I'm being a bit. I've created a variable W. Actually, I'll even be more complicated. W. Let's go underscore R.
What does it mean?
Yeah, I'm just actually making it obvious that it's a. What's that? That's real wage change function, just one way of describing the Phillips curve. Just to show you, I can do a notation in Minsky as well. Okay, then I've got the integral block. Copy that, and I say the current wage, multiply the wage change function, integrated, is the wage change function. And I need the initial value for the way, which I haven't put in here yet, so W underscore R underscores 0. Let's see how that works out. And 0.8. That's all I need to define the model. With the beta, by the way, if you want to move everything over, you can just click and drag like that, select everything and then drag it over like that, relocate on the screen. That's not possible with the earlier versions. And now that's all you need to finish the model, because I've got the wage rates multiplied by labour. I get the wage bill, which I'll call capital W. I've got output up here. So output minus wages becomes profit, which I'll call Greek pi, capital PI. That's going to be investment underscore G for gross, because it's investment before you subtract depreciation. Okay. Now, you don't have to make it a circular model, but one trick in Minsky is if you right-click on an object and call flip, you flip it 180 degrees. Okay, and then I've now got IG going this way, and then I need to subtract depreciation, so I need to have capital. Copy of that. That's now flipped the wrong way, so I've got to flip that back. Okay. Multiplied by depreciation, so a copy of that. That's also in the wrong direction, so I flip that again. Multiplied by. Subtract depreciation from gross investment, and you get net investment, which I'll call I underscore N. Wire that up, and now I attach that up to K, top of the K block. I haven't got K0 there, so I've got to add that, K underscore 0, and I said to make that 300. Make that a parameter as well. Copy that, attach that to the bottom of the integral block, and this Y is ugly, so you just click on the blue dot and drag it like that. Equally, you can just pass by Y. I mean, I'm just showing you what can be done with Minsky here. I'm not necessarily doing the best thing to lay out a model, but that's just one way of doing it. You can instead, I'll delete that wire, simply take a copy of IN, put it up over here, flip it, recenter the model so I can actually see it, and drag it in the top. So I don't need to have the wire up there. Okay?
YN is not necessary. Right?
Pardon?
IN is not necessary.
No, it's necessary. It's over here. I don't have to do. Iron's defined down here. I could drag a wire up, but I can just put the name there instead.
Yeah.
Okay.
You could also just put the wire next to the minus and then take care of the right.
Huh?
You can also just put the wire from the minus.
Yeah, that's fine. Yeah, that's absolutely not necessary. Yeah, just a way of laying things out more, hopefully more neatly. So whack a couple of graphs in. What I suggest graphing is the employment rate. Take a copy of that. And the wage rate. Take a copy of the real wage. And then make an XY chart, graph the two together. So take a copy of employment, whack that on the bottom, let's say attach that to the green wire, and the wage rate, copy of that, attach that to the vertical green wire, and look what you get. Okay. It's the same basic dynamics you saw for the predator-prey model. So Goodwin's intuition was correct, and so was Marx's.
Why do you attach these things to these specific places on the line?
Yeah, let's show me. Hang on.
No, it's just a question.
Only comes from
Okay, you got the bits and pieces. Okay, please want to...
The question is simply why do you put the wires on these places?
On the bottom, okay. Because we're trying to make it easy to make XY charts. You've done an XY plot in Excel, for example?
Sure.
Okay, it's a plane. What we have to do with Minsky is each of the four wires here are the same colour as the first four there, and each of the four wires here are the same colour as the last four up here. So if you want to make an XY chart, all you have to do is attach something on the vertical to the same colour as something on the horizontal. It'll plot X against the Y. Okay. And you can actually do 8 of them, which would be crazy, but you've got that flexibility. So it's just trying to make it easier to create complicated charts. We're going to go a lot farther with the charts in terms of appearance and control in the next year or so. Okay, cool. So what you've got is a cyclical model. Now, at the moment, of course, you've got the abstraction. There's no change in population, no change in labour productivity. Okay, which is wrong. Pardon me. So one way you can do this is, I'll bring up the magnifier here. One of the commands on the right-click menu on a variable is add integral. So if I choose that, I have A as an integral down here. So I can now say there's a rate of growth of technical change. And if I multiply, I now bring another variable which I'm going to call alpha. For the rate of technical change, I'll make that a parameter. I could make that a variable as well and say technical progress occurs at 2% per annum with a maximum of, say, 6%, minimum of 0, step size of 0.01. And now if I want to get technical change, I multiply the current value of labour productivity by that rate of growth, integrate it, and I need an A0, an alpha 0, or an A0 as well, so I type A underscore 0 here, give it a value, say, of 1, so one worker per unit of output. I'll make that into a parameter. Copy that. Add that to integral block. Same thing for n. So I'll define, say, beta for the rate of growth of population and give it a value, say, 0.015, so 1.5% population growth per annum. Maximum 0.03, minimum 0, step size 0.01. And I need an n0 as well. So the value to m0 is the value I gave to n initially, which is 120. Give yourself a range of values there. And now if I go to n, same stroke and right click, choose add integral. Bring it down here just to make things neater. And I then have beta I've still got beta as a parameter. I'll change it as a variable of accident. I'll make it into a parameter. Again, in a more complicated model, you could make population growth depend upon other factors. So beta is now a parameter. Beta multiplied by n. With n 0, again I've forgot to make that into a parameter. It just doesn't really matter, I can run the model anyway. Now I run the model again. Notice I've got a growing wage. Real wage is rising. So I need to define a new variable, which would be, say, the wages share. So I take a copy of W, divide it by Y, and call that omega, which looks like W itself, which is a flow. Wire that up, take a copy of that. Oops, hang on, I flipped it by accident. It's very simple. The action is done on what they call mouse up, by the way. So if you move the mouse when you're trying to choose something, you'll choose a different menu item. And I'll take a copy of that and replace it over here as well. And there's your cyclical model. Okay? I think that's a good time to stop. We'll come back and